This is an ABC podcast.
Catching planes. Remember that? In the past 30 years, flying, which was once a thrilling and glamorous experience, became pretty commonplace, even boring. But every time you entered the big tin can that would be propelled through the sky by roaring jet engines, you could have a reasonable expectation of safety. Flying is much safer than driving, we all know that. But built into all of that is the assumption that thousands and thousands of precision-engineered components are all operating within tolerances of a fraction of a millimetre. Simon Winchester can see how the story of the modern world is really a story of precision, of ever-shrinking tolerances, which began with the steam engine and are now operating down at a subatomic level to create machines that can detect the faintest gravity waves arriving here from distant galaxies. And yet for all that, Simon is wondering whether the modern obsession with precision has gotten completely out of hand. Simon Winchester is the author of a book called Exactly: How Precision Engineers Created the Modern World. And I recorded this conversation with him a few years ago at the Canberra Writers' Festival. Simon, your father was a precision engineer. Tell me about the winter's evening in London when you were a boy, when your father introduced you to the magical properties of highly precise objects.
He had a factory in North London, and he would bring things home for me from time to time. And I remember vividly this one. I must have been about 10, I suppose. And he came with a box, a beautiful wooden box with his name, B.A.W. Winchester, Esquire, inscribed on a sort of brass plate on the top of it. And he opened it up, put it on the table. My mother was preparing dinner, and the dining table was laid, I think. And he opened this box, and there were these, turned out to be 101, I think, pieces of steel, highly polished steel, ranging from about an inch cube down to a sort of a tablet, and then a small billet, and then a sort of feuilleton, if you like, as they got smaller and smaller and smaller, until the ones at the very end were just sort of wisps of steel. And he explained that these were things called Joe blocks or Johansen blocks, and they were used to calibrate micrometers, which he used a great deal of in his factory. So he took out two of them, the two biggest ones, and laid them on the tablecloth. And this exercised my mother to a great degree, because she was from Belgium, and she was specifically from Ghent, the industry of Ghent being lace making, and she had made this beautiful white Simon Pure, I think I can legitimately say, tablecloth. And my father was always irritating her by putting things that were covered with a thin film of machine oil on them. So he put them, my mother sort of gave a little cry. And then he said, "Boy, I want to demonstrate, first of all, that these things are not magnetic, because they're made of steel." And he pushed them towards each other, and pushing them on their oily backsides, my mother just shrieked and left the kitchen. She didn't want to see any more of this. And he pushed them towards each other, and they didn't either repel or attract each other. So having proved that, he then put one on top of the other and said, "Okay, lift the top one up." So I lifted it up, and the bottom one came with it too, which was a bit odd because they weren't magnetic. And he said, "Separate them." So I, with my right hand on the bottom one and my left hand on the top, tried to prise them apart. And they wouldn't come and wouldn't come and wouldn't come. And I tried, and I sweated and whatever. It proved impossible to break them apart. And then he took them and he said, "That's what I wanted to demonstrate. It's easy to separate them. You just slide them like that. It's called ringing, W-R-I-N-G-I-N-G. But you can't pull them apart because they are so precisely made, so flat, that they actually molecularly bind with one another. And it is a feature of ultra-precision which fascinates me," this is him talking, "and I hope one day will interest you." So his life, in a way, was central to my early thinking about this kind of thing, and it seemed an obligation to honour his memory. that I should write about precision, and so the book is dedicated to him.
Was there something deeply emotionally satisfying for him and for you in the absolute, almost perfectly, precisely flat surfaces of those blocks?
Well, the idea of making something perfectly flat is central to all engineering, really, because you have to move lathes and drills and various mechanical devices along very flat surfaces in order to achieve the kind of things you want to achieve when you're making anything, from a widget to a jet engine. The person that invented the concept of flatness, which is a very difficult thing to achieve, was this man called Henry Maudsley. He learned how to make things that are perfectly flat.
And how do you do that? How do you make something so perfectly flat?
Well, it's easier than you would think. If you get 2 blocks of steel that you think are nearly flat and rub them once against another, you'll see that there are bumps and dips and hills. And the only way you can make certain that those are eradicated is to bring in a third one into the process. And with using 3 things, you grind and you drill and you polish and you burr until all 3 things mesh against each other impeccably. And then all 3 are perfectly flat.
And hence your father's satisfaction. I suppose what I'm getting at is that you say that increasingly the modern world is kind of fetishizing this idea of absolute precision. Do you have that yourself? Can you enjoy that feeling like your father enjoyed that feeling?
Well, no, because I cherish and relish imprecision. After all, I'm a writer. I use fountain pens. I wind clocks. I delight in things that are imprecise. I'm not a very good woodworker, and wood, of course, is something you can never make precise because the wood itself is very imperfect. I mean, it swells and it twists and it bends. You can only do precise things with metal and ceramics and electronics, of course. But no, I relish the imprecise, but I'm fascinated by the precise. And looking at those steel blocks and wondering why if they're so flat, how can they stick together? What is it that's at work that allows them to do so? It intrigues me.
You started your working life as a petroleum geologist, and you were put in charge of dropping, this is the life you've had, Simon Winchester, you were put in charge of dropping a drill rig in just the right spot in the North Sea. How did you drop it where it needed to be dropped?
Well, it was called the Orion, and it must have been, it was what was called a jack-up rig, which is, you see them floating on the surface of the ocean, and they have these enormous iron legs, which what they have to do is to drop the legs until most of them are anchored into the seabed, and then the rig itself jacks itself up a couple of 100 feet, or 100 feet above the surface of the sea, and then they start drilling. So when they've finished drilling a well, they have to move it to another location where they think there's likely to be gas, as in this case, this was 1967, I think. So what am I then, 23 years old, I'm really wet behind the ears, and I'm put in charge of a Dutch tug, that is tugging this drill rig to a point in the North Sea on a winter's day, raging, it was bad, bad weather. The people in Chicago had said, we need to put this rig exactly on top of this dome in Permian sandstone, deep down there, where we think there might be gas.
At the bottom of the North Sea?
At the bottom of the North Sea. It's a crazy business. So here I am, talking by radio to the tool pusher, who was an enormously obese man from Louisiana, up on the rig. And he knows he's dealing with some limey, just out of school, if you like, who's on the radio to him, telling the tug driver to move, he's got this enormous, it weighs about 8,000 tons rig, move it back 50 feet and then to the left, or port left 20 feet and then starboard 10 feet. And then you have to give this order, which is an irreversible order, to drop the legs, because then explosive bolts go off. And you see these legs rocketing down to the seabed, and you know that once they're down, this is a rig that costs $10,000 an hour to operate. So if you've screwed up expensively, and the people in Chicago will be very, very cross. So I was talking...
They have guns in Chicago too, don't they?
They have a lot of guns in Chicago, a lot of mean people over there. So up on the rig, they said, are you sure? And I said, I'm sure. Because I'm looking at, back in those days, it was pre-GPS. There was something called Decca Navigator, which there was a station somewhere in Norfolk and another one in Hilversum in the Netherlands, one in France, 3 signals. And so you knew more or less where you were, nothing like today. Drop the legs, you saw the puffs of smoke, and suddenly the legs start down, splashing, red rust everywhere, and the legs were there, anchored to the seabed. And then everyone on the rig calculates exactly where we are.
And how close were you to the drop spot?
It could be an embarrassing moment. 200 feet away, which was not bad. I mean, they said, that's acceptable. And what had happened was that when I gave the order to drop the legs, I was on the right spot, but it took about 5 seconds for the legs to drop, and the current underneath took the rig a little bit to the north. But the satisfying thing was that they struck gas about a week later. So I was sort of vindicated. So I never did it again and never wanted to.
Well, that was then. That's the 1960s. And you're still using some kind of system to triangulate locations. But now that we have GPS, how much more precise is that business of being in a boat, some kind of vessel, in you're bobbing ocean waves with no visible real landmarks, dropping a rig, having its legs go bang down to the bottom of the ocean floor. How much more precise is that business now?
Well, I was on a Japanese survey vessel a couple of years ago that's run by an organization called JAMSTEC, a Japanese atmospheric meteorological survey vessel. And they use 12 satellites, not 3 and not 3 Decca Navigator stations. And they can get their position in the Northwest Pacific to within 5 centimeters. So it's pretty incredible. And incidentally, people used to say of GPS that the Pentagon insisted that there was a deliberate error put into the GPS signals, which, as you probably know, are sent out of, or at least managed out of a place in Colorado. And it used to be said they put in a 100-meter error so that you couldn't, let's say, send a missile to the White House or the Oval Office.
So there's a deliberate error coded into...
but that was what they used to say. And President Clinton, issued an order saying that GPS should be available to everyone. We say, I mean, we have GPS, but nobody pays for it. I mean, the American government pays for it. But it is not true. There never was an error deliberately inserted into this GPS signal by the Department of Defense. And as you probably know, there are other GPS systems. The Chinese have one. The Europeans have one called Galileo, to which the British are now going to not have access if Brexit goes through on Halloween. So we'll have
to be crashing your cars everywhere. And,
exactly. Yeah.
A couple of years ago, I went to Iceland for the first time, and I didn't have data on my phone. And so I had to do, being in Reykjavik, I had to do something I hadn't had to do for quite a while, which was actually to buy a map of the city centre, use that to navigate around and get an overall picture of the city in my head. I was surprised by how much I'd missed doing that, how pleasurable it was, and I still have a map of Reykjavik in my head today. What's been lost with GPS?
An immense amount. I think it's, for me, and I'm glad to hear what you've just said, I mean, the joy of maps is incalculable. I love the things. The book I'm working on at the moment is all about land ownership. And I'm going back to Scotland, where some of the research I'm doing involves 3 islands: the island of Eigg, the island of Ulva, and the island of Rasay. And Rasay, back in 1965, I was in my second year at Oxford, and one of the things you have to do when you're reading geology is that you have to map 6 square miles of somewhere in the United Kingdom, produce a map of the geology of somewhere. And I chose almost at random the southern part of the island of Rasay and I got it out. I mean, I've kept the paper I wrote. And I lived in a roofless croft. I cooked over a primus stove, incredibly lonely, except I could be sure that every time I went out with my geological hammer and my clinometer and my compass and my little bottle of hydrochloric acid, if I did that on the Sabbath, on a Sunday, an islander would come up and say, "Oh, Mr. Winchester, you're not supposed to be on the Lord's Day, with your hammer go back and rest, and reflect.
He was right. Go back and lie in the hay in your roofless croft. And,
exactly, and suffer the rain that the good Lord has sent you. Right? But the map, it was such a joy to produce. It's more or less right. And what we lose is the joy that you had in keeping Reykjavik in your head, which GPS you've no idea about.
And yes, yet I use it all the time for convenience sake. There's so much precision behind the modern world. What are the invisible aspects of this absolute bang-on precision that have become an essential part of our lives?
Well, good Lord, where does it stop? Where does it start? GPS is a classic example, but the steam engine, let's start with that. So we're the starting point. Precision has a birth date. We know when the very first precise thing was ever made. It was born on the 4th of May, 1776, so 2 months to the day before the founding of the United States of America. It was born in North Wales on the 4th of May. The steam engine had already been invented by James Watt. The simple fact that water, when heated to 100 degrees Celsius, undergoes a phase change, turns into a gas, which is 1,760 times bigger than the water. So from that, you can get work. So how do you do it? Well, you have an engine with a piston and a cylinder and a variety of gears and so forth, and a source of heat and a source of fuel and a water to turn into steam. So what did all of that? Well, what he couldn't do was make a proper cylinder. You took us, in those days, 1775 and prior, to make a cylinder, you took a sheet of iron and hammered it and hammered it and hammered it until it formed a rough circle, and then you welded it together, turned it vertically, lowered your piston in it, set everything to work, and as you might imagine, with a cylinder made like that, steam went everywhere. It was highly inefficient. It just produced a lot of wasted energy.
He couldn't even get near the machine, could he?
No, you couldn't, because you'd be scalded. It was extremely dangerous.
So it was this huffing and puffing behemoth with covered in this cloud of scalding steam, and it didn't create that much energy
it
either.
was sort of useless. But the theory was entirely right. 70 miles away to the northwest, near Denby, was a man called John Iron Mad Wilkinson. John Wilkinson was a lunatic, a certifiable lunatic.
John Iron Mad Wilkinson.
Iron Mad because he loved iron. Why, I have no idea. He had a lot of it. He had an iron ore mine, but he used to puddle it and hammer it and do all sorts of things. He made a desk out of it. He made a table out of it. He made a boat out of it. He made a coffin out of it. And this was before the Me Too movement really got underway. He used to, whenever a comely lady was apparently coming to his workshop, he would lie, I believe, fully clothed in his iron coffin, and when she arrived, spring out to surprise her. Jolly japes, Well, he's buried in that coffin today under an iron obelisk. But he made money in the 1770s by making cannon for the Royal Navy. And he had developed a technique of boring a piece of iron with a drill mounted on a very flat surface. This is where flatness comes in, so that it wouldn't wobble as it advanced towards and drilled a hole in the piece of iron. And the hole that resulted might be only 6 or 8 inches in diameter to accommodate the cannonball, was more or less straight and more or less true, so that the cannonball would fly out of it when the charge was applied. So he was tired of turning this drill manually. And he heard of this man, Watt, who had made an engine that in theory could do this. So he invited, today he would pick up the phone and call Watt, but in those days he sent a letter and said, would you come bring all the components for a steam engine that will allow me to drill into these pieces of iron to make cannons for the Navy? So Watt assembled all of the bits he could, including the cylinder made as I've described, and the piston and the gears and all the rest of it. Put them in a horse-drawn wagon, took them up to Denby, and he made the machine, filled it with coal, filled it with water, lit the coal, and the thing started moving. But you can imagine Wilkinson standing with his arms folded, saying, you just don't know. You don't get it, Mr. Watt. Rubbish, exactly. Had a Welsh accent, I think.
Oh, okay.
And he said, I'll show you how to make a cylinder. How big do you want this piston? How big should it be? And he said, well, for a big engine, let's say 36 inches in diameter, and a little bit to accommodate the piston. And so they got an enormous piece of iron, a big, very hard drill, and on this very flat surface, bored into it. It took about a week. But ultimately, there was a hole in a piece of iron, 36 inches and a little bit in diameter. He lowered the piston into it, and it fitted like a glove. And they fired it up, lit the fuel, water boiled, chuff, 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 chuff. No steam left at all. The thing was impeccably, precisely made. And with that, on the 4th of May, 1776, truly the Industrial Revolution was born, because Watt said to Wilkinson, "This is marvellous, I'll have 500 more cylinders." And instantly, factories all over England and Wales and Scotland, so in cities that really weren't cities at all, places like Birmingham, Liverpool and Manchester and Glasgow, suddenly manufacturers had the ability to harness the power of steam to turn things, to make things. From my point of view, I wanted to know the tolerance between the inner edge of the cylinder and the outer edge of the piston that enabled it to fit so closely. And they knew that the specifications that Watt was to make, or Wilkinson was to make these cylinders to, was that they would fit to the thickness of an English shilling of the time. And an English shilling was 1/10 of an inch. So I figured that this, because my editor was skeptical about how to organize all this information, so I said, begin the book with things that have a tolerance of 0.1 of an inch, and then the next chapter, 0.01, 0.001, 0.00001, right up to today, where, ironically, the most precise mechanical thing or physical thing that is made by humankind now is also a cylinder. There are 4 of them, 2 of them in Washington State, 2 in Louisiana. They're made not of iron, but of fused silica, and they are at the beating heart of what are called LIGO. I don't know if anybody knows what LIGO is. The Laser Interferometer Gravitational Wave Observatory. They detect slight changes in the shape of the Earth if, as Einstein predicted in 1906, a gravitational wave passes through space-time continuum because of the collision of black holes or something like that. Everyone thought, well, this is an impossible thing to measure. But LIGO people, NASA, National Science Foundation, figured it was possible if you build big enough interferometers. And at the heart of the interferometers that have now successfully detected 5 gravitational waves are these cylinders. They're beautiful things to behold. They're held in springs and all sorts of torsion balances and things. But they are made, the surfaces are so flat that they can detect changes in length of 1/10,000th of the diameter of a proton. And that is the diameter of a proton is 10 to the minus 15, add another 4 zeros for 10,000, so 1 times 10 to the minus 19.
Look, it's not a lot. It's not a lot. So you're saying this is a machine that currently exists in the world that can measure an almost vanishingly subtle effect created by a black hole light years away, and to do so, it measures a tiny oscillation in the shape of the entire Earth.
That's exactly right.
My God. I feel that's quite dizzying and delightful and wonderful and a bit troubling as well at the same time. I wonder why.
Well,
I'm so troubled by that.
I went to the LIGO Observatory in Hanford in Washington. Do you all know what an interferometer is?
Of course we do. Yes. We do.
Well, I mean, if you listen to Richard's program,
this is an engineering conference, I was told, isn't it?
Well, very, very basically, if you can imagine 2 very long arms, exactly 90 degrees, 4 kilometers long actually, and they fire. You've got a sort of prism where my chest is. And you fire a laser into that prism, which breaks it into 2, which travel down to these cylinders that I mentioned and gets reflected back again. If the 2 tubes are exactly the same length when the laser beams are fired, then the 2 beams will come back together. And if they're in phase, then they'll simply reinforce each other. It'll be a bright white light. If, however, during the firing of these things, because of a change in the shape of the Earth, one of the tubes becomes microscopically shorter than the other, then the two light beams will come back and will interfere with one another. That's why it's called an interferometer. And they will show bands of colour instead of white. Very easy to detect. It's a very simple process. But the dimensions of these changes are so minute that you have to have very, very precise equipment to measure it.
This distant cosmic event caused this faint ripple that took millions of years to reach the Earth, and just made the whole world go like that, the tiniest way. It's a bit like, in some ways, I suppose, the glass of water in Jurassic Park that starts to tremor when there's a T-Rex coming along.
Right.
So it's like that.
It's just like that.
Just like that.
The wonderful thing was that Einstein predicted it, theoretically, and a century later, about 2 years ago, he was right. He was proven right. I mean, it's the majestic vindication of one of the classic theories of physics.
Podcast. Broadcast and online. You're listening to Conversations with Richard Fidler.
One of the key aspects of the development of precision is the concept of interchangeability. Now, I think I'd always imagined that had always been with us, but it hasn't. Tell me how the concept of interchangeability in manufactured precise objects was arrived at.
Well, probably the best example is of flintlock guns that were being made both in Britain and America, and crucially in France. And there was an engineer, a gun maker in Paris, who was producing these things. And at the time, all guns were made by hand, so that if your gun exploded on the battlefield, you had to go to the armourer and get a totally new gun, which was expensive and relatively difficult thing to achieve.
So they were disposable guns, I suppose.
Well, sort of, but jolly expensive. Yeah. So this man decided, he broke the gun down into, there are 10 component parts in a flintlock. There's the trigger, of course, and the thing that strikes the spark. It's called the frizzle. And then there's the pan, which holds the little piece of stone, the flint, that actually creates the spark that ignites the gunpowder. And he decided that he would make every single one of these parts exactly the same. And he would devise a machine for each part that would make each part exactly the same. And he invited, crucial day in the 1780s, all the grandees of the French military and, crucially, Thomas Jefferson, who was the American minister to France, to see this demonstration. And what he did was, he said, it's very easy to make a flintlock. I mean, I'll show you how. And he assembled the 10 parts. And he said, now, there's a box, 100 triggers, there's a box of 100 frizzles, there's a box with 100 pans, there's a box with 100 this, that, the other. Take any piece from any box and you can assemble them because they're all the same. And lo and behold, they all were the same. And the guns all worked impeccably, which prompted Jefferson to write a note saying, this Frenchman has just created an amazing new phenomenon. And I think, as we are in sore need of guns, being America, of course, this fact should be transmitted. So the Secretary of War ultimately put out a contract, and within years, not many years, huge new armories had been created in Harpers Ferry in Virginia and in Springfield in Massachusetts, close to where I live, which churned out, using the principle of interchangeable parts, to create millions of weapons and enabled America to become a great fighting power and also a great industrial power. Because the American way of producing factories or making things in factories based on this principle took over the world. And a good example of that comes in the manufacture of cars.
When you get to the manufacturing of cars, your book has 2 examples. And there's Henry Royce, the founder of Rolls-Royce, and then there's Henry Ford, of course, the founder of the Ford Corporation. Both of them had a commitment to absolute, gorgeous, exquisite precision, but in different ways. Can you explain the difference there?
And there's an important difference. I mean, both of them born in 1863, both of them obsessed with mechanical locomotion, and they both had the Dion quadricycles, which are effectively 2 bicycles bolted together with a 2-horsepower engine, incredibly noisy, no brakes, very dangerous, but enormous fun. So one of them in Michigan and one of them in Lancashire or outside Manchester, driving these things and saying, this is the future. We've got to make these things work properly and be safe and comfortable. And so Henry Royce decided that what he wanted to make was the finest automobile in the world. And so he set up a factory in Cook Street in Manchester and produced innumerable models of cars. But at the same time, this fellow Henry Ford said he had a sort of almost evangelical approach, rather different view to Royce's. His view was that this country is so amazing. You've got the Grand Canyon, you've got Maine, you've got Badlands, you've got all these wonderful things to see. Everyone in America should have one of these machines to go out and visit the wonders of this country. So I'm going to make cars that are available to everybody. And the two machines that I look at closely are the Rolls-Royce Silver Ghost, which was manufactured from 1908 to 1928, and the Ford Model T, which enjoyed almost exactly the same longevity from 1908 to 1926. They made 8,000 Rolls-Royces and 18 million Model Ts. The difference being that the Rolls-Royces, precision was important, but they were handmade. And so if the tolerance of a particular hole in a casting was not right, the engineer could file it until it was right. But Henry Ford, in order to make millions of these things, had to rely on this principle of interchangeable parts. He set up this factory in Dearborn in Michigan, and all the component parts of a car, whether it's parts of a carburetor or a brake or the steering wheel or the wheels or whatever, were in hoppers on the second floor, and they would come down from the hoppers to the assembly line, this new idea of an assembly line, and piece was put in the carburetor into the right spot in the car, and the line moved on. If, for some extraordinary reason, the piece coming down the hopper was not precisely made, was not truly interchangeable, then it wouldn't fit. The assembly line would grind to a halt. All the men would stand around smoking and cursing, but earning money still. And the company would lose money. So there was this imperative that everything had to be made perfectly. So the difference in the ethos, if you like, was Royce wanted things made perfectly, expensively, because as time went on, the cost of labor became greater, whereas the reverse happened. A Model T in 1908 cost $850. In 1926, it cost $260. So economies of scale took over as well, all things which are central to modern manufacturing. But of course, the interesting thing is that of those 8,000 Silver Ghosts that were made, 6,000 still exist and are in running condition, whereas of the 18 million Model Ts, virtually all of them have ended up in the scrap heap or in razor blades.
Rolls-Royce became a brand synonymous with excellence, and of course its jets are on the planes that so many of us climb into and fly around the world in. You cite the case of the famous Qantas flight from 2010, QF32, which the pilot was Richard de Crespigny. He was on my program some years ago talking about this experience of when one of the engines exploded. Tell the story of that in terms of how this is really a story of precision taken to such an extent whereby the slightest error can mean catastrophe.
Well, and I start looking at the idea of whether both mechanical and electronic precision are reaching the limits of our abilities to either to make them or for these things to be sustainable. And the case of QF32 is a good example of that, because, as you'll remember, it was the inboard, the portside number 2 engine of a fully laden A380 with 450 souls on board, I think, coming out of Singapore, headed for Sydney. 7,000 feet over Indonesia, the number 2 engine blew up, and the shrapnel went all over the place, damaged the wing horribly. Mercifully, didn't enter the passenger cabin, didn't cause decompression of the aircraft. And thanks to the heroic efforts of Crespigny, and there were 4 other pilots, it was an unusual flight in that regard, they wrestled the aircraft back to Singapore, and they dumped as much fuel as they could, and they landed it 300 feet from the end of the runway. All the brakes, of course, there were no brakes on the left-hand side, and the wheels were white hot, and fuel was gushing out of the left-hand wing. I mean, it was a formula for not so much disaster in the air, but disaster on the ground. But eventually everything was brought under control, and then they examined why the engine had failed so catastrophically. The center of the engine has these whirling compressor blades made of a nickel alloy, but they operate in a temperature which is about 300 degrees Celsius higher than their melting point. So why do they not melt when they're going round and round and round? And they don't melt because engineers, largely at Rolls-Royce, devised a system of pumping cool or relatively cool air into the blades themselves, and through a very complex network of tiny little holes punched in the surface of these blades, a thin film of cool air surrounds them as they whirl round and round and round, stops them from melting. I mean, it's almost so difficult to believe. And I'd been to the Rolls-Royce factory on this particular day and got sort of irrationally excited about this. I mean, I thought it was an incredible technology. So that night, I was at a big black tie dinner at my old college in Oxford, sitting opposite Marina Warner, who's an expert on the worship of the Virgin Mary, the American ambassador to Bulgaria, who was on my right, and a leader writer from the Times. And I was going on in this sort of slightly irrational way that I'm going on to you about these amazing holes and cool and all the rest of it. And they were sort of politely interested, as you are. Maybe you are as well. And then there was one of these awkward silences at a dinner table where nobody is talking, except that the master of the college, a chap called Roger Ainsworth, said, "Actually, Simon, I invented that technology." And he had been. It was a wonderful moment. I reinforced my gratitude for going to that college.
But it seems like the nature of these inventions that they seem so terribly precarious the way you describe it. Like if someone said to me, I've got to fly up to Sydney tomorrow, mate, we're going to put you on this thing that's powered by a jet. It's going to be spewing out this kind of aircraft fuel and be powered by these rotating compressor blades. They're going to be rotating at a speed that actually would normally make them melt. But don't worry, mate, because we're going to blast them with cool air. We're going to blast them with cool air from this little funnel thing. It's going to be fine. You'll be fine. You'll be fine.
Well, and that brings the point of what caused this accident, which is there's a tiny pipe called an oil feed stub pipe, which is about the diameter of a drinking straw and about the length of my little finger. And it was very, very thin and had been mismachined in a factory. And the people in Sydney, they monitor the engines all the time, in real time by people. And they were unaware that there was this potential for fatigue in this little tiny tube. And turns out that the plane in question, QF-32, had taken off from Los Angeles en route to London, heavy load, shortish runway, and the thing had been under immense stress but didn't break. The next leg from London to Singapore was a fairly light load. The tube was under no stress. But then from Singapore to Sydney, they spooled up the engines very, very rapidly to do a very sharp ascent to 7,000 feet. This put the tube, which had been mismachined 1/100th of a millimetre too little, a tiny, tiny hair's breadth too little, and it caused that spot of weakness to fracture. Hot oil spewed all over these blades, and it instantly flashed into fire, which raised the temperature of the wheel where they're based. It made it wobble and break, and then all the blades themselves became pieces of shrapnel. So one has to wonder whether our machining of mechanical components of such minute dimension, with walls that are so thin that 1/100th of a millimetre can be the difference between life and death, is, for potentially 459 souls, and is yet something we should worry about.
And yet, so much of modern life is that we get on a plane like that, thousands of such planes take off and land successfully, where these little tubes have not been misaligned by a hair. It does work nearly all the time, to the point where flying by plane is much safer than driving anywhere. And what is it?
You're absolutely right.
What does this tell you about the modern world? Well, it's very odd, isn't it?
It tells me that the modern world is based on a knife edge of precision, if you like, because, look, all the manufacturers, look at what's happened to the 737 MAX. Their manufacturers are pushing the ability of these planes to go faster, to go higher, to take more passengers more economically. And some things, in this case it's software, in the Rolls-Royce case it was hardware, they're pushing the limits, possibly dangerously because of commercial pressures. And all I say is that we should be wary. That do we need to go an extra 5 miles an hour faster when we go to London? Is it important for the companies and the shareholders that they push the need for profit that much. But nonetheless, it's something we should consider. And the same goes for electronic precision. As you probably know, in an iPhone 8, the heart of this is an A4 chip made in Taiwan, which is about as big as my little fingernail. Well, on that chip, there are 4 billion transistors, not million, but billion transistors. There are so many, they're so tiny, they can fit 4 billion into each iPhone. There are more transistors in the world today than there are leaves on all the trees in all the world. It's an unbelievable number. You're beginning to wonder if they're going to reach levels of where their behavior becomes impossible.
Yes, I mean, given that the LIGO device you were talking about earlier, which measures the tiniest bit of planetary wobble that operates within a tolerance of a bazillionth of the width of a bee's bit of male genitalia.
It's not exactly how I put it. It'll do.
I think you'll find it's a far more accurate description of distance.
But not precise.
I mean, given that it's that tiny, like a tiniest fraction of a proton, as you say, have we reached the limits of precision now?
Well, no, according to the engineers. And computer engineers say, well, there's quantum computing, there's optical computing, there's many avenues to go down. Soon, ones and zeros, binary computing will seem old-fashioned as a horse and cart.
Then we're entering the quantum realm there, where everything gets strange and things can be in two places at the same time. Precision is getting to the point of weirdness now.
That's exactly right. I mean, Schrödinger's cat and all that sort of nonsense will be brought into play. But it was at that point that I thought, well, wait a minute. Are we fetishizing precision? Is it, in fact, perhaps not ultimately necessarily good for us all? I mean, good Lord, I'm not a dinosaur in these matters, and I relish precision where it's valuable. But are we forgetting the values of craftsmanship and the joy and the beauty of the imprecise? And that's what took me to my wife is a Japanese-American, and so we go to Japan a lot. And it occurred to me that Japan is a society which, in these matters, keeps its feet very firmly on the ground. Yes, Japan produces things which are astonishingly precise. I mean, Nikon and Canon and all the rest of these companies for which Japan is so very well known. But they also produce beautiful things made of bamboo and of lacquerware, and their woodwork is impeccable, not precise necessarily, but good for purpose. And so I went to Seiko. Seiko, the word means precise in Japanese. They invented the quartz watch, the quartz movement, which they never patented, and so all sorts of makers, Casio and people like that, make quartz watches, which will tell the time to hundredths of a second. If anyone wants to tell the time, I'll meet you at 12:34 and 6/100ths of a second. Not something you ever do. So I
then
went.
You send a text saying I'm running 5 minutes late. Yeah.
5 microseconds late, yeah. So they have a factory in a place called Morioka in northern Honshu, and I went up there, and they took me up to the second floor where they have the line where they're producing movements, largely for export. And it's a robotically controlled sort of tiny little production line, because they're producing tiny little things, but I think 25,000 a day, so 1,000 an hour, of these super, super precise quartz movement with effectively no moving parts. And they could see that, because they knew why I was there, that I was a little disappointed and sort of unfazed or unimpressed by this. They said, well, come with us. And so we went to another area, also on the second floor, and there were heavy doors which shut behind us. And you enter an area of cathedral-like calm. You can't hear the chattering of the production line. And there are about 20 or 30 men and women, all wearing white coats, all sitting at desks with tweezers and magnifying glasses and intricate little pieces of equipment, assembling by hand mechanical watches with mainsprings and hairsprings and jewels and things like that. And that is a line of which you scarcely see them in shops because they don't sell. They're called Grand Seikos, and they are mechanical watches which year after year after year win all their horological awards that are held in Switzerland. They beat all these fancy things you see advertised on the back of The Economist, Patek Philippe and things like that. They are junk compared to these beautiful mechanical watches that are made by Seiko.
By what standard, though? Are they as accurate as the quartz watches made in the other part of the factory? Or if not, how are they better?
They're not accurate at all. They lose 5 or 10 seconds a day. They're hopeless because who cares, really? We're in the normal sort of social intercourse. You don't care if people are 10 seconds late. I mean, who really wants to know time, except if you're a space capsule or things like that.
And a radio presenter, yes.
And yes, of course, a radio, you're absolutely right. I live in this old farmhouse in Massachusetts, and I have 8 mechanical clocks in the house, and a barograph, which is, as I'm sure you know, a clockwork apparatus which records on a paper trace on a brass drum the rises and falls of atmospheric pressure in our little village. And my parents gave it to me in 2001, and I've therefore had it now for 18 years, and have got stacks and stacks of these traces showing that hurricanes have come through, and rainstorms and snowstorms and stuff. So every morning, every Sunday morning, I wind all my clocks and the barograph. It's a ritual which I do at about 7 a.m. on a Sunday before I get the paper and have my coffee and all the rest of it. And all of Sunday, all of Monday, the clocks are all in harmony with one another. They all strike on the right hour. By Tuesday, they're starting to fall out of rate. By Thursday, it's a complete shamble. But I'm reminded of that wonderful book by Dorothy L. Sayers. And Dorothy L. Sayers wrote this book called Gordian Night. And she talks about walking back from a meeting through Oxford on a summer's night, and it's midnight. And I listened, she said, to the college clocks chiming midnight in friendly disagreement. And I love the concept of friendly disagreement.
You mentioned how in Japan the Seiko factory prizes the making of these non-quartz watches, these beautiful mechanical watches. I wonder if there's something about the ultra-precise modern world that increasingly leads people to seek refuge in that kind of aesthetic. Like, more and more our living rooms are designed to Scandinavian and Japanese ideas, which are based on asymmetry and biomorphic lines and natural lines and timber and lacquer, all those things like that. What do you think of that?
Well, once again, having a Japanese-American wife, I mean, the whole concept of wabi-sabi is very important.
What is wabi-sabi?
It's the joy of, if you like, the imprecise, of the natural line of a tree. I mean, there are no straight lines in nature. I mean, the horizon isn't straight, although you may think it is. And from that, you get joy in things that are built to human scale. Initially, all measurement was done to human scale. I mean, the earliest measurement is the cubit, which is the length of a pharaoh's arm from his outstretched finger to his elbow. And then the inch is the thumb, and the foot is obviously what the foot is, and the yard or the pace is, mille pasus, 1,000 paces, where we get the word mile from. And then it was regarded as nonsensical because people are different sizes and shapes. And so measurements started to be done according to some degree of physical objects. And so the French and the British largely devised a system of measurements with standards against things were measured. There was the standard kilogram, there was the standard meter. And they're all housed, or were all housed, in the basement of a mansion outside Paris in Sèvres, where the porcelain is made. And the grandees of the measuring world, the metrology, not meteorology, but metrology, meet every so often.
There's a conference about this?
Oh, they're so enthusiastic, you wouldn't believe. And
I've never been invited to that conference. It's a secret meeting that's held in France.
With secret symbols.
Right, all of that. And they decide what a kilogram or a kilometre is?
They do, but they would, and they've all been abolished because now everything is measured electronically according to states of decay of krypton atoms or radon atoms. And one by one, these physical objects, which are things of great beauty. One of them, I dare say, is here in Australia. It must be. Because all the countries that were signatories to the agreement have copies of the standard kilogram and the standard meter, basically. One by one, they were abandoned until the last one, the standard kilogram, which is about the size of a Zippo cigarette lighter. And it's kept under 3 glass cloches, sealed into a vault, seldom, 6 keys all held by different people, different families. No one can touch it, but every so often, every 20 years or so, things are measured against it. And the terrible thing is that the one in Paris is losing weight.
How? There's no one feeding it properly, is there?
That's it. Little bubbles of air apparently are escaping from it as they, as it were, rise to the surface. It sounds quite implausible. So the one standard that people are now absolutely focused on is the second. How long is a second? The principal research being done on the nature of the second is actually being done in Beijing. Believe it, it gets so esoteric.
But what do you do for a living? I'm in charge of the seconds.
But the charming thing is that outside there's a grove of apple trees, and one of them has a little plaque at the bottom saying this apple tree, which produces juicy red apples, was presented to the Metrology Institute of China by the National Institute of Standards or Physics in Teddington in West London. And it's taken from a graft from Walsingham Manor. It was the graft from the tree under which Newton sat when the first apple dropped, and he thought, what is the force that's impelling that to fall? So there's a lovely symmetry.
I'm advised that we have precisely 19.26 seconds left for this program. All that's left for me to do now is to ask you to please thank the wonderful Simon Winchester.
Thank you very much.
That conversation with Simon Winchester was recorded live at the 2019 Canberra Writers' Festival. Simon's book is called Exactly: How Precision Engineers Created the Modern World. I'm Richard Fidler. Thanks for listening.
You've been listening to a podcast of Conversations with Richard Fidler. For more Conversations interviews, please go to the website abc.net.au/conversations. Discover more great ABC podcasts, live radio and exclusives on the ABC Listen app.